Hi, welcome to another video. So in this video, we're going to talk a lot more, about how to use some of these inverse functions that we just learned about, namely sine inverse, cosine inverse, tangent inverse, and a little bit about cosecant, secant, and cotangent inverse. So let's just refresh a little bit about what these things mean, maybe a slightly different look at it. Remember that when we're talking about a unit circle, sine of theta equals y, or the y coordinate of some point on the unit circle for whatever angle theta is. And cosine of theta equals x, and tangent of theta equals y over x. Now, what that means is that their inverses basically undo that. So sine inverse of y equals theta says this: if your input is now the y coordinate of some point on the unit circle, sine inverse of that y coordinate is going to give you the angle that creates that point with the y coordinate of whatever it is. This was also exactly why we had to define whatever our domain of sine was to create a one-to-one function, because obviously we know that we can have a y coordinate that's the same at both an angle that's smaller and larger if we go from the x-axis, a smaller angle and a larger angle, one in quadrant 1 and one in quadrant 2, if that y coordinate is positive, that would create a problem. And so we've defined these on very, very specific domains so that the inverses actually work. So we have a one-to-one function that lets us map forwards and backwards. So what this says is that we can use the unit circle as long as we remember that sine, cosine, tangent take in angles and give you out the y coordinate for sine, the x coordinate for cosine, or the y over the x coordinates for tangent, for whatever angle you plug in. The inverses reverse that. The inverses say, as long as we remember that the y coordinate for sine inverse, the x coordinate for cosine inverse, or the y divided by the x coordinate for tangent inverses as the inputs will give you out the angle that creates those points, but only on 2 out of the 4 quadrants. So for sine and sine inverse, the quadrants are 4 and 1, negative pi over 2 to pi over 2. For cosine, cosine inverse, those quadrants are 1 and 2, 0 to pi. For tangent, it's 4 and 1 again, but it does not include negative pi over 2, it does not include pi over 2. That's why we have parentheses or these inequality notation without the equal sign. Now, in a little while, we're going to do some stuff with cosecant inverse and secant inverse and cotangent inverse, and they match up pretty good where they're defined. So the domain, or actually the range for this, our range for cosecant inverse is only valid for the same thing that sine inverse is. So from negative pi over 2 to pi over 2, wherever that's defined, there is a vertical asymptote in there, so we have to be very careful. And thankfully, secant inverse is defined on the same exact interval as cosine inverse is, provided it's defined. Now, cotangent is a problem. Cotangent inverse has a different range for our theta than tangent inverse does. And so that is an issue. So whenever we're working with tangent inverse, we oftentimes will use, well, what do you think? Cotangent inverse is paired up really nicely with cosine inverse. And so those actually work very well. We're going to see that in a lot of examples. When we get there, that sometimes we can have a little workaround if we're struggling to find an angle for something. So we're going to get into it. We're going to learn all about how these inverse functions really give you out an angle. And that's the whole point. So let's take a look at sine inverse of the square root of 2 over 2. Right there. I really need in your head that what this gives you out, what this says is, hey, the y coordinate is square root 2 over 2. Give me the angle that creates that. That's what sine inverse is doing. Sine inverse says, plug into me a y coordinate, and I will give you the angle that creates the point on the unit circle with that y coordinate. I will give it to you from negative pi over 2 to pi over 2. Why? Because that's the one-to-one part of the function that we defined our inverses on. So we're going to say, this gives you out an angle. Now we can really do something with that. We could actually go right from here and say, hey, if we really understand how to use our unit circle, if we really understand that sine inverse is only defined from negative pi over 2 to pi over 2, then really what I'm looking for is the angle that gives me a y coordinate of the square root of 2 over 2. So I'm going to look at that. Notice how there is no repeat of y coordinates on this part of my unit circle. That's why we defined it. There would be if I included this. That's why we didn't include that. So square root of 2 over 2 happens only right here at pi over 4. So that angle is pi over 4. Theta is pi over 4 for sure. Now there's something else that we can do to show a little bit more math. Some students really like doing this, some don't. So take it as you will. It doesn't really matter to me. But here's one thing that we can do. If we understand that sine inverse of y coordinate gives me angle matches up with sine of angle gives me y coordinate. Sometimes seeing that makes it easier for students. Either way you go, it doesn't really matter. This is just putting it in something that a lot of students are more readily able to see. It's like, okay, I'm looking for an angle that's giving me a y coordinate of square root of 2 over 2. Are you really doing anything different? No, you really aren't. You're not doing anything different there. So however you go, whether you understand that's the y coordinate, find me the angle. Okay, pi over 4, or sine of what angle gives me square root of 2 over 2. Again, that'd be pi over 4. We have to stick to the correct range for our inverse functions, domain for our trig functions. So no matter what, we get pi over 4. Now here's the next question. What I'm getting you to understand is that sometimes we get some weird stuff like this, and I'm walking you through that right now. I'm walking you through like how you would do this is understand that that is, man, that's a y coordinate of a point. This is creating for me the angle, or finding for me the angle. Then cosine can ask about that angle. So could we find cosine of the angle you just found? Well, yeah, sure. Cosine of pi over 4 is also square root 2 over 2. And that's precisely what this asks you. So what this part says is find cosine. Okay, what do you plug into cosine? You plug in angles to cosine, and angles to sine, and angles to all of our original trig functions. So cosine needs an angle. Does this give you an angle? Yeah, it does. This says find me the angle that has a y coordinate square root 2 over 2. We've already done this. So this is exactly what this is talking about, and it's exactly the process of going through it. So whenever you get these kind of weird things, what in the world are they asking you there to do? They're saying find the angle from this inverse trig function, then find cosine or whatever that trig function is of that angle. It's honestly not that hard to do as long as we remember what in the world inverse trig functions are doing. They're saying, find me the angle that gives me this particular y coordinate for sine, x coordinate for cosine, and y over x for tangent inverse. That's what it's doing for you. So this says, hey, you could find cosine of this is the angle. That's why we defined it that way. It was really nice to do that. So this gives you an angle. If I wanted to find cosine of this, remember, these two things are equal. Sine inverse of square root 2 over 2 is the theta that we were talking about. This is cosine of pi over 4, and that is square root 2 over 2. And that's really all there is to it. So we're going to practice several of these. I'm not going to walk you through it this way anymore. I'm going to just give you this and say, here's the thought process I'm going through. It's exactly this structure. This is talking about an angle. Find the trig function of the angle. Just make sure you are on the right domain for your trig function or range for your inverse trig functions. We'll see that in just a second. Let's move on. So we're taking a look at tangent of cosine inverse of negative square root 3 over 2. What the heck? What does that even mean? Remember what these things do. Tangent needs an angle. Think about what cosine inverse does. Cosine inverse is going to give you out an angle. This was the big deal here, saying regular trig functions give you in angles, give you out coordinates of points. Inverses say, plug in coordinates of points, I give you out angles. So this is going to give us out an angle. So the first thing we're going to do here is take the inside. If it's an inverse trig function, understand this is going to give me out an angle. Call it an angle. Call it theta or something, and then find theta. There's two ways to go about doing it. For some of you, it's going to be really easy to look at this and go, okay, I understand that cosine talks about x coordinate stuff on a unit circle. So cosine inverse is saying this is an x coordinate on some point on this unit circle, restricted to 0 to pi. So can we look at this? Can we look and say, hey, from 0 to pi, find me something with an x coordinate. Remember, this is x. an x coordinate of negative square root of 3 over 2. All of our x's are positive here. This is quadrants 1 and 2. So an x coordinate right there, that's an x coordinate of negative square root 3 over 2. The angle that causes that is the output of our inverse trig function. So this says, find this angle. This is talking about an angle here. This is saying, here's the x-coordinate, find an angle that gives me that x-coordinate on 0 to pi. That's how we define it to get a one-to-one part of this. I hope it's making sense to you. This is 150 degrees, or we probably put 5 pi over 6. We always use our radians for our inverses. So our angle is 5 pi over 6. What that means is this thing in here is 5 pi over 6. You see, we set this equal to the angle. We just solved the angle. We can make a substitution now. This is this thing. So what this all boils down to is you've now found the angle that causes that x-coordinate. Now find tangent of that angle. Well, that makes sense because tangent needs an angle to give me some sort of an output. We can do more work if you need to. You can do a couple other things here that would be of benefit to some people. Sometimes we can say, all right, if this is true, then cosine theta equals negative square root 3 over 2. You can find theta. It'd be exactly the same, but maybe it's a little easier to look at. You go find cosine of what angle gives me that x-coordinate restricted to that domain. Well, that would be negative square root 3 over 2. I'm sorry, 5 pi over 6. But either way, we get that. Also, some teachers like you to show that because you called that theta, that you can write tan of cosine inverse of negative square root 3 over 2 as tangent of theta, but we now know theta. Personally, that's a little bit of overkill for me, but some people like to show all that work. The way that I would normally do this is identify this as an angle, use your unit circle right from here, find the angle, and then because this is equal to this thing, you can substitute that. It's a direct substitution, you get right down to here. And then we'll perform that trigonometric function. Tangent of 5 pi over 6 is asking you, well, here's 5 pi over 6. Can you find tangent of that angle? Tangent relates to the y over the x coordinate. So 1/2 over negative square root 3 over 2. If we get that, we're going to get negative 1 over square root 3. Or negative square root 3 over 3, which is exactly what this is equal to. So it's kind of a long process if you do show the work. Hopefully it's not a hard process. Hopefully you are making the connections that inverse trig functions give me out angles. Trig functions need angles as inputs. So this output becomes the input for our trig functions. It becomes an angle for our trig functions. I hope that works for you. I hope you're really seeing that. So we're going to do 3 more examples, 2 or 3 more examples. I'll show you what to do when they're not on a unit circle, and then we'll switch it around. We'll say, what if we have an inverse of a normal trig function? All right, here we go. So we have secant of sine inverse of negative 1/2. Right in your head, right now, think secant requires an angle as an input. We look inside. Okay, is this an angle? Sine inverse. Inverse trig functions give you out angles. So if we evaluate that, we are going to have an angle out. That's what this says. Sine inverse says, I'm going to give you out an angle. Well, now let's think about that for a second. If this gives us out an angle, then this has to be some sort of a coordinate on somewhere, on a unit circle, hopefully. But what coordinate? Well, sine inverse says, instead of plugging in an angle and me giving you out a y coordinate like sine does, sine inverse says, give me the y coordinate, I'll give you the angle. So sine inverse matches up a y coordinate to the angle that creates that. So sine inverse says, this is a y coordinate. Find me the angle that makes that y coordinate. That's what that's going to give you out. So how do we do that? Remember that sine inverse is only valid from negative pi over 2 to pi over 2. So we're in quadrants 4 or 1, but using negative angles here. And so what we're going to do is understand that, hey, a y-coordinate of negative 1/2, let's see, y-coordinates are positive here and negative down here. Negative 1/2 is right there. Do not use 11 pi over 6. Don't do that, because that's not in there. You have to use negative angles here. So sine inverse of negative 1/2 says, find me the angle that gives me a y-coordinate of negative 1/2 on this part of your unit circle, from negative pi over 2 to pi over 2. But they are using negative angles, so that would be negative pi over 6, not 11 pi over 6. Well, that's pretty good news, because now we understand what that part is. This said, here's my y-coordinate, find me the angle, and we just did. This angle is equal to whatever's inside that function right now, whatever's in secant. This thing is the angle we just found, so we can rewrite it. And now that's something that we can do. Also notice that even though secant inverse is only defined from 0 to pi, it is okay for us to find a regular trig function of negative pi over 6. We're not finding an inverse of secant right now. We're just performing a trig function. Secant is defined, well, on the entire domain, except where we have these vertical asymptotes, and it's not at negative pi over 6. So we can go ahead and find this just fine. So secant of negative pi over 6, well, this is going to give you 1 over cosine, or 1 over x. And so you can do it that way. So here's negative pi over 6. Secant is the reciprocal of cosine. So that would be 1 over square root 3 over 2, or 2 over square root 3. That's totally fine to do that as well. If you needed to show this and get 1 over square root 3 over 2, that's 1 over x. You can get that, that's fine, but you'll immediately reciprocate and multiply. You'll get 2 over square root 3. Yes, we're going to rationalize this. We're going to get 2 square root 3 over 3. That's about all there is to it. We're using inverses to find an angle and then evaluating a trig function of that angle. The outputs of our inverses are angles. The inputs of our trig functions are angles. It works perfectly. Hope it's making sense. I hope you're understanding that even though our inverses are restricted to certain domains, as long as we don't get anything undefined, our trig functions are just fine with whatever angle we get out of that. It's perfectly okay to do. And so here we just like, yeah, negative pi over 6, and then secant is 1 over x, or the reciprocal of cosine. So I'm thinking cosine square root 3 over 2, the reciprocal is secant, and that would be 2 over square root 3. Let's move on to another one. So we're taking a look at cosecant of tangent inverse of the square root of 3. All right, well, let's start out. Let's start off with the inside of that parentheses and figure out what tan inverse square root of 3 actually means. What tangent inverse is going to give you, just like every inverse trig function, it's going to take something to do with our coordinates and give you out an angle that creates that. So just remember what tangent deals with. Tangent deals with y over x. So tangent inverse is going to say, you give me that. You give me that y over x. And I'll give you out the angle that makes it. That's my output to you. It's an angle. And so we would think, all right, tangent inverse of square root of 3 equals angle. What angle gives me a y over x of square root of 3? Sometimes, as I was saying, it's easier for people to think of this. Tangent of what angle gives you square root of 3. That's especially useful if you have a table. So I do this all by unit circle, but sometimes you can get a table that says tangent and cosine and sine of all, and cosecant, secant, and cotangent, of all these very normal angles. And this will be on there. And so you look through and go, okay, tangent of what gives me square root of 3? If you like this way, do it that way. If you like this and say tan inverse of what angle gives me this y over x, or this same thing, tangent of what angle gives me y over x, either way you go with the same question. I hope that you're seeing that. These are no different. But this is easier to use with the table because this is on there directly. So we think and go, all right, it's got to be pi over 3. Because pi over 3 is, number one, it's on the correct interval for our inverses to work. Tangent inverse only works from negative pi over 2 to pi over 2, not including those two n values. But the only place where on that interval we're going to get a positive relationship of square root of 3 is when we compare this y, square root of 3 over 2, divided by 1/2, because the 2's cancel, and we would get that out. So that angle is pi over 3. Either way you go, your angle is pi over 3. And it worked well. Tan inverse of square root of 3 gives me out an angle. Now we're going to evaluate cosecant of that angle. Because this angle equaled this inside of our function, we can substitute and say now we're going to find cosecant of whatever angle we found. So cosecant takes 1 over y, or reciprocates the y coordinate. Why does it do that? Cosecant's related strongly to sine. So sine is the y coordinate, cosecant is 1 over the y, or the reciprocal of the y coordinate. So we're going to take a look at that right now. Cosecant of pi over 3 says, here's pi over 3. Remember, it can be anywhere on a unit circle for the trig function. It does not matter. You do not have to restrict it, but cosecant of pi over 3 says find your y coordinate, take 1 over that, or reciprocate it. So here's my y coordinate. I'm going to take 2 over square root of 3 again. If I rationalize, we get 2 square root of 3 over 3. All right, let's take a look at this one. Cotangent of cosine inverse of negative 1/2. We're going to go fairly quickly through it, understanding that inverses give you out angles. So let's write this as that relationship right now. Understanding that cosine inverse of negative 1/2 is going to give me out an angle, but it's only going to do so where cosine inverse is defined. Where cosine is defined to give me a range for cosine inverse of 0 to pi. So only on quadrants 1 and 2. So let's take a look at this. Let's understand that cosine is relating an x-coordinate and an angle together. Cosine of the angle gives me x-coordinate. Cosine inverse of the x-coordinate gives me the angle. So let's find that x-coordinate, but only on this part of my unit circle. So my x-coordinate has to be that one right there. That's negative 1/2. That's on this 0 to pi where we restricted that to get a 1-to-1 function. So negative 1/2 for x, yx, let's deal with cosine. What angle creates that? Well, it's going to be 2 pi over 3. If we want to show it this way, sometimes that's a bit easier. Cosine of what angle gives me an x-coordinate of negative 1/2? Now this is really clear because we know cosine is equal to the x-coordinate for whatever angle that is. Cosine of what angle gives me that? Still, you get 2 pi over 3. By the way, sometimes you'll have students who really want to use a calculator here because your calculator will perform it, but they're probably not going to give you that. It's going to give you a decimal out. Some do, and that's really nice, but it's very beneficial to make sure you can use a unit circle. So refrain from using your calculator unless you absolutely have to. So we're thinking, hey, cosine inverse x coordinates, deal with the x and the angle. Our angle that makes that x coordinate on the appropriate domain is 2 pi over 3. Now we're going to find cotangent of 2 pi over 3. That's what this thing is. It's the angle. We just found the angle. So now evaluate it. So cotangent of 2 pi over 3, let's see, tangent is y over x, cotangent is x over y. So we're going to go right back to that angle we just found, 2 pi over 3, and we're going to evaluate cotangent, the x over the y. So negative 1/2 over square root 3 over 2. If we reciprocate and we multiply, we get negative 1 over the square root of 3. If we rationalize, that's negative square root 3 over 3. So I hope I've made it very clear on what we're doing here. Depending on what inverse trig function we are, we set up what interval on the unit circle we're in. Sine inverse and tangent inverse deal with negative pi over 2 to pi over 2. Sine includes those n values. Cosine is the odd one, the cosine inverse from 0 to pi. Actually, cotangent is 2. We'll get that later. But we restrict that. We find out the appropriate angle that's giving us the y-coordinate for sine inverse, the x-coordinate for cosine inverse, or the y over x for tangent inverse. That gives us an angle, then we evaluate the trig function of that angle. I hope that's really clear. I hope I've explained it to you in such a way that that makes sense. I'm going to come back and I'm going to show you what happens when these things are not on a unit circle. We're going to have to draw some triangles. Not that hard, and it's super valuable for calculus 2. All right, so let's take a look at something like sine of tangent inverse of 1/2. We think, all right, we got this, right? Sine needs an angle, tangent inverse gives us an angle. That's great. That's exactly what we want. Inverse trig functions give out angles. That's their output. So let's set it up that way. Okay, well, here's what this is asking. I want you to think of tangent. Tangent is y over x. Now, tangent inverse says, take that y over x relationship and give me the angle that creates that. And you go, well, wait a minute. Tangent of 1/2 is, I don't see that 1/2 for a comparison of y over x on the unit circle. And that's true, that's not there. And so what happens is, this is one of the reasons I was prefacing that if tangent inverse of 1/2 equals theta, this is only if tangent theta equals 1/2. Now before, when we were on a unit circle, this was really easy. But when we're not, this is really helpful. So if you are not finding this out very easily, you're like, I don't know where that is, we'll write this as a normal trig function. So we're thinking, that gives me an angle. That's true. This is not on a unit circle. It's also true. So let's write this as, hey, if tan inverse of 1/2 gives me theta, tangent of theta gives me 1/2. So what's that mean? Well, tangent takes a relationship of an angle to the y over x coordinates. So wait a minute. On a triangle, this would be y over x. Okay, let's draw a triangle like that. You see, that's what a unit circle did anyway. It was basically subscripting these triangles onto this circle. So let's make a triangle out of this, where a y is 1 and an x is 2. So we can do that, provided that we're in the right quadrants. So remember what tan inverse does. Tan inverse says, I only work in quadrants 4 and 1, from negative pi over 2 to pi over 2. So you have to obey that. Otherwise, you'd be able to draw two triangles here. For instance, a y of 1 and an x of 2 would put a point right there. That would be a relationship on a right triangle with a y of 1 and an x of 2. But you could get the same exact relationship if you did -1 and -2. Do you see that? Do you realize that -1 divided by -2 is also positive 1/2? So why wouldn't we use that triangle? Right there. That's the entire reason. Maybe it's the first time it's really clicking, is that we had to eliminate like half of the unit circle, or half of our xy plane, if you will, so that we don't have this situation where we could possibly get out two different angles. That's why we restricted it. So when we're dealing with inverse trig functions, you're in only one of two quadrants. You're either in 4, 1, negative pi over 2 to pi over 2, or you're in 0 to pi, one of those sets of two quadrants. So for tangent inverse only works in these two quadrants. That's exactly what this says, negative pi over 2 to pi over 2. So that means this is not okay. So our relationship says, yes, tangent inverse is 4 or 1, the only place where both x and y are positive for tangent inverse to work is quadrant 1. That's why we draw it there. Now, can we go a little further? Can we take and, wait a minute, that's a right triangle. I hope you're seeing that tangent of theta equals 1/2 says your y is 1, your x is 2. That gives me a right triangle. Could we find the hypotenuse? Well, wait a minute, it's a right triangle. That's awesome. So right triangles say, yeah, if you can take x squared plus y squared, it's going to equal r squared. For whatever hypotenuse you have. That's Pythagorean theorem. Well, now let's plug in some values. Please, for goodness sakes, don't forget to take square root. Super common. So people go, oh, it's 5. Take the square root, we get a square root of 5. So by the Pythagorean theorem, leg squared plus leg squared equals hypotenuse squared, we know that that hypotenuse is square root of 5, or that this would be like on a circle with a radius of the square root of 5, not a unit circle, a square root of 5 circle. Not a thing. Now, why in the world would we do that? Well, to answer that question, you see, if we're not on a unit circle, we have to basically reinvent the wheel, so to speak, for every different radius. It's not 1. The unit circle is great because with the radius of 1, we got a lot of very common angles and their respective points. That's great. Well, do you have a circle like written out with a radius of square root of 5? No, I hope not, because that'd take forever to do all the possible radii. That's impossible for us to do that. And so what we do is we go, okay, let's invent just the one angle that we need that has this relationship. So bear with me, here's like a 20-second recap. We take our inverse trig function, we write out equal to an angle. If this is on a unit circle, this is pretty easy, because we go, okay, tangent inverse of what's the y over x, find me the angle that gives me that. Even if you write it this way, tangent of what angle gives me y compared to x. On a unit circle, pretty nice. If it's not, then we're going to create the one triangle to find the one angle that we need that has a certain radius, with a certain y and a certain x. So we can draw it. As long as we remember what tangent does, tangent relates y to x. Draw a picture in the appropriate quadrant. In this is quadrant 1. Our y is 1, our x is 2. We can complete that triangle with Pythagorean theorem every time. And now, here's the magic part. Tan inverse of 1/2 equaled an angle. This is that angle. So if you find sine relating to that angle, you're going to solve this. So let's go over here. Let's understand what sine is. Sine, if you remember, was y. But what did it really mean? It meant y over 1. Or y over the radius, the opposite over the hypotenuse. This is the main reason why a long time ago, when I introduced what sine really was in the unit circle, I said, remember that sine of theta is y over r. Cosine theta is x over r. Tangent theta was y over x. If you remember anything about right triangle trigonometry, you remember that tangent theta is opposite over adjacent. Sine was opposite over hypotenuse. Oh, there it is. There's our r, y over r. Cosine was x, or adjacent over hypotenuse. For whatever right triangle we have. Also, I want to mention, you use the signs here. So sine, not like that sign, but positive and negative. You have to have that because we're working on an xy coordinate plane. We have to have the ability to have negative x values, negative y values. So for us, now that we've found that, now that we've said we've got a picture of this angle, we have a picture of what this gave us. This angle that we're talking about is that angle, and here's the way the triangle would have to look if we have a comparison of y to x of 1/2. That is the angle. Now find sine of the angle relates back to says, find sine of whatever angle this is giving you. This gave you an angle relationship amongst these sides, just like that. So find sine of that angle. Sine of the angle we just created takes, well, let's see, y over the r. Normally, it's just y, because our r is 1 for a unit circle, but here it's not. So that plays part of it. So y over r says take your 1, that's your y, over your square root of 5. If we rationalize that denominator, we're going to get square root of 5 over 5. Now, I know it's kind of weird that we actually never found the angle, but that's not what it's asking. It's not asking you really for the angle. It's asking you sine of that angle equals what? And that's what we found. So that's kind of neat that without even knowing what that angle is specifically, we can relate a triangle that answers the question of sine of that angle. So it's kind of a workaround. This is why we had to draw the triangle, so that we can relate these two sides and how sine wants you to do it for whatever angle tangent inverse of 1/2 is gonna get you. That's the idea here. I hope that makes sense. We're gonna come back and do a few more, but the plan is if something's on a unit circle, it's easy to find the angle and you can actually find it explicitly. Then find the trig function at angle, it's not a problem. If it's not on a unit circle, you won't find the angle explicitly. You'll draw a triangle that relates sides in the appropriate way that represents that angle. Then you find a trig function of that triangle. So for sine, that was opposite over hypotenuse. No problem, and that's what we get. All right, let's try this one. Tangent of sine inverse of 1/3. Think about what sine inverse wants to give you out. It wants to give you out an angle. So what we're going to do is say, all right, the first thing we're going to do every single time is say that sine inverse of 1/3 wants to give me out an angle. If that's on the unit circle, you can do it right from right here. Or if it benefits you a little bit, sine inverse of 1/3 equals theta, if and only if sine theta equals 1/3. Now, for a unit circle, you're perfectly okay doing it here. If it's not on a unit circle, you kind of need this one. Why? Well, because this is showing you how an angle is related to two sides on a right triangle. So this is saying sine's giving you a y over an r, or this vertical part of your right triangle compared to your hypotenuse, or the radius on some sort of circle. Because sine inverse only works from -pi/2 to pi/2, we're going to put this on our xy coordinate system appropriately to represent just one point and not 2 points. You see, here's the thing. We can put this on our unit circle, and this will always be the case, in 2 places. That's why we had to restrict this to half of a unit circle, or half of a xy coordinate plane. So if we have a positive y value of 1, and a radius. Remember what sine theta does. It says y is our vertical and r is our radius. We could do one of 2 places. If we had a 1 with a radius of 3, we could be either here or we could be over here. You'd have a radius 3 going this way or a radius 3 going this way. Both of those points would be absolutely valid. Those both have a positive 1. Those both have a radius of 3. They would both represent an appropriate angle. So which one's right? The one that's in the right quadrant, the one that's in the right domain for our sine to be 1 to 1. That would be just from -pi/2 to pi/2. This is in quadrant 2. Sine inverse does not work there. Sine does not work there to give you sine inverse, so this is wrong. This is not what we want. I hope it's making sense to you at this point. Why in the world have we restricted that domain? I know it probably did before, but now you're really seeing why. Because otherwise, we can't do this. You'd have 2 angles. That's a really big problem. And so we think of it this way, think this is going to give me out one angle. Relate that. Okay, where does it have to relate? If y is positive and the radius is positive also, the hypotenuse is positive, that's got to be quadrant 4 or 1. Well, down here, y would be negative. So we're in quadrant 1 for sure. By the way, this is obviously not drawn to scale. It's just a graphic representation of what we want to show. Now that we have that, let's find x. Let's find whatever this x value would be, and that's going to be Pythagorean theorem every time. So leg squared plus leg squared equals hypotenuse squared. No problem. We can have x squared equals 8. And ultimately we get x is this 2 square root 2. Now is it valuable? Well, yeah, absolutely it's valuable because this gives me a way to look at this angle. So sine of theta is 1/3 says, here's the triangle that matches that. I don't even know what the angle is. I don't even care. This is the angle. We just found it. It's right there. And this is like the one time in math you can go, find x, and you go, there it is. Find theta, there it is. It's like right there. Like this is the triangle that gives you that particular angle. So we found the angle. Now when we ask the question, can you find tangent of the angle? Yes, tangent using this angle as what this is giving you, because that's what it gave you. This gave you an angle relating y over r, you found the x. This is the one and only one triangle that would have that angle, and the only one angle that would have this particular triangle with these particular y values and hypotenuse values and x values. So tangent says, now let's work with that. So tangent is, look at the angle that we just got from the triangle we just created from this inverse trig function and give me what tangent does. Tangent theta is y over x. That would be 1 over 2 square root 2. If you rationalize that, we get square root 2 or 4, and no, you can't simplify it. Don't simplify that. That'd be bad news. But that's it. This is what we're looking for. You're looking for what tangent of an angle is going to give you, a relationship among sides. We just found it. You don't even really care about what the angle is. Now, we could do this with our calculators, but that's not what the idea is. The idea is, give me the relationship among sides, y over x, for an tangent of that particular angle. That's what we're doing. That's what we showed. Oh, that's so close. Don't you think that was a little 2? If it was a little 2, we'd be done. Almost done, because that would be on the unit circle. But it's not. So let's go through the process. We know that inverse trig functions give angles. Start with that. This is only true. Cosine inverse of negative square root 3 over 3 gives you theta, if and only if cosine theta equals negative square root 3 over 3. Now we look at a unit circle. Can you find me an angle on a unit circle where the x-coordinate is negative square root 3 over 3? You go, no, I can't do that. Then draw yourself a triangle with this relationship, that this is giving you x over r. Cosine can be viewed as x over 1 or as x over r. Well, that makes sense because if the radius is 1, we just get x. That's true. So cosine gives you x over r. But we also have to play along with where cosine inverse is defined. See, this, where its range is really, this only works if that angle is between 0 to pi. So if this is x and x is negative, notice, and r is positive here, we have a couple of choices. We can do a negative x, positive r up, or positive r down. But because this would be in quadrant 3, I can't do it. Cosine inverse only works from here to here, 0 to pi. So here would be positive x, here would be negative x. You'd have to be in this quadrant. I hope that makes sense to you. I hope you're seeing why we restricted it and how it's so very important to understand that. So let's do negative square root 3. We don't have to be really to scale here. You just need to know your quadrant. So our quadrant is, because x is negative, I'm on this half of my y-axis or my xy coordinate plane. And because of that, I know that cosine inverse is only 0 to pi. It's got to be up here. So our x is negative square root 3. This is why we had to allow for these negative values so that it puts us in an appropriate quadrant. And our r, or our radius, or our hypotenuse is 3. Take the time to go ahead and find out what y is. I always write y, x, and r because it makes the Pythagorean theorem work a little bit better for me. So length squared plus length squared equals hypotenuse squared is negative square root of 3 squared plus y squared equals 3 squared. And we're going to solve that for y. Negative square root of 3 squared is 3. So negative squared give you positive, square root of 3 squared is just 3. So y is going to give you the square root of 6. Now this is super valuable because what this gave you was an angle. And based on the triangle that angle gave us, that this gave us, we can find cotangent of that triangle. I should say really cotangent of that angle using the triangle we created. So inverse function gives me angle out. That angle is this angle right there. The only way that this triangle is created from the angle or the angle from the triangle in this relationship is if this is the angle we're talking about, and now we find cotangent of that angle. Don't even need to know the angle, I just need to know the triangle that creates it. So let's think of cotangent theta. Cotangent is the reciprocal of tangent. So tangent was y over x, cotangent is x over y. So cotangent of this angle says, I want you to put the x over the y. And we make sure that we use sines. So if we deal with that, most of the time what we do is we see if we can simplify these square roots before rationalizing. I'd make one square root, that's going to be the square root of 1 over 2. Well, the square root of 1 is 1, but the square root of 2 we would rationalize. And we would get negative square root 2 over 2. Well, that's exactly what this is equal to. This caused angle, angle created a triangle. Since it's not on the unit circle, we're not finding the angle specifically, like explicitly finding that. We're finding the triangle that is made from that angle using this relationship amongst x coordinate, or the x side, and the r, or the hypotenuse side of our triangles. Then we find a trig function from that triangle. And this says this whole thing is equal to negative square root 2 over 2. I have one more. I know I'm doing a lot of examples, but it's because I want you to really get good at this and really see it as the appropriate quadrant based on how your trig functions are defined as far as your inverses are concerned. So back with one more, then we'll start going backwards. What happens if you have an inverse of a trig function? It's a little bit easier. Okay, last one before we start going backwards. So sine of tan inverse of negative 3. Tangent inverse is going to give you out an angle. Let's start with that. This is only true if tangent of the angle is equal to negative 3. These are both true statements of one another. So tan inverse of negative 3 equals theta if and only if tangent of theta equals negative 3. Now, let's think about this. Can we find an angle that gives me negative 3 when I compare y over x on a unit circle? No, there's no negative 3. I can't find that on the unit circle specifically. So we're going to draw a triangle from this. Now remember, there's always two places where this is going to be true on a unit circle. However, only one place if we use the appropriately defined domain for tangent. So this has to take place between quadrants 4 and 1, negative pi over 2 to pi over 2. And maybe think about it this way. Where is tangent negative? Tangent's negative in quadrants 2 and 4. Which of those quadrants works in this? Well, only quadrant 4. This is off limits. You can't do it there. So if we're going to say, hey, tangent theta relates y to x, then that would be a y of negative 3 and an x of positive 1. Y of negative 3, x and positive 1 would be, here's a y of negative 3 and an x of positive 1. Now you might be thinking, how in the world would you get something up here? Well, you understand with fractions that negative can go to the numerator or denominator. So you could do a y of positive 3 and an x of negative 1 and get the same point. But that's in quadrant 2, and tangent is not defined there. Tangent's only defined for inverses only on 4 or 1. That's why we had to choose that. That is probably the biggest thing I have to talk about. You need to absolutely make sure you're following that, or this stuff is going to explode. So we're in the appropriate quadrant, not that one, this one. Tangent's still negative there, that's fantastic. We have a y value -3 and x value +1. So let's keep going with our setup. We've got a y value of -3, an x value of +1, and we can go ahead and we can find that r. So we know that Pythagorean theorem says leg squared plus leg squared equals hypotenuse squared, or x squared plus y squared equals r squared, no problem. So we can do that. And that would give us a square root of 10. Now, one thing I've been neglecting, I want to show you right now, when we take a square root, we typically do a plus and minus. And that actually is really relevant because we want to make sure that we're in the right quadrant. So what would it mean if we had a negative square root 10? This negative radius, what that would do is flip that about our origin. So that would create this other radii going kind of in quadrant 2 instead of quadrant 4. So we want to do that. We want to keep this in the correct quadrant. So we're going to keep this as positive square root 10. But please notice something, that sometimes when we take a square root, if we're in like quadrant, let's say 2 for cosine inverse or something, and we need to find the x value of that, well, then when we take a square root, we want to keep the negative, not the positive. You need to make sure that you're in the correct quadrant. That's a really big deal. So here we have this r of positive square root 10 that keeps us in the right quadrant. It's quadrant 4. And now because that angle is giving us that triangle, we can find sine of theta using that triangle to find it. So sine says, I want you to take my y over my r, or my opposite over my hypotenuse, or my -3 over square root 10. Use the signs, it's really important. If we rationalize, we get -3 square root 10 over 10. That's exactly what this equals. So we're done. Let's go backwards a little bit. Let's start finding inverse functions of some original trig functions like sine, cotangent, cosine of these values, and then find an inverse of those. It's a little bit faster, and the reason is because these things are defined everywhere where there's not a vertical asymptote on your unit circle. So there's really not an issue. These are all going to be very easy to find. You don't have to worry about that. And then when you do the inverse, just make sure you're on the appropriate portion of that unit circle and you're going to be set. So we're going to do that. We'll come back and deal with some more cotangent inverse and cosecant inverse and secant inverse, which we don't see that a lot, but I'm going to show you how to work with that. And then we'll call it a day. So in order to deal with these, there's not going to be a lot of triangle drawing, anything like that. All we really have to do is figure out what sine 5 pi over 4 is and find cosine inverse of that. So deal with your inside first like before. It's just easier because we're more used to these normal trig functions, and they'll all be something that are defined. You don't have to worry about restricting that right now. So sine of 5 pi over 4, we know that sine of 5 pi over 4 is going to be this y coordinate of the point where that angle creates on a unit circle. So 5 pi over 4 is, let's see, right there. Sine is negative square root 2 over 2. And now we think of cosine inverse of negative square root 2 over 2. Remember that this is going to give us an angle. So cosine inverse of negative square root 2 over 2 asks, now it's where you restrict your domain, on the appropriate portion of your xy coordinate plane or your unit circle, basically from 0 to pi. On 0 to pi, where is your x coordinate? Negative square root 2 over 2. Right there. That would be 3 pi over 4. If it helps you to do that, that's fine. This says cosine of what angle gives me an x coordinate negative square root 2 over 2. Like I was saying, this is very, very useful for a lot of students because this puts it in your head like, oh yes, I'm looking for the x coordinate. It's sometimes easier to see. The angle would still be x coordinate of negative square root 2 over 2 on the appropriate domain. For that to be a one-to-one function, for the inverse function to work, would have to be just 3 pi over 4. And that's really about it. So this is going to give you an angle, and then this asks cosine inverse of that. Sorry, this is going to give you a coordinate, so angle, this gives you a coordinate, then asks what angle creates that coordinate for you on the appropriate part of that unit circle. How about the next one? Tangent inverse of cotangent of 2 pi over 3. Find this part first. Now, cotangent of 2 pi over 3, it's not a vertical asymptote right there. This should be pretty easy to find. So use your circle and find that. Cotangent of 2 pi over 3. 2 pi over 3 is right here. Now, if you're thinking, well, wait a minute, tangent inverse isn't defined there. Who cares? Cotangent is, and that's all we're talking about right now. We're going to deal with the inverse function after we figure that out. So it's not to worry right now. Don't worry about it. Figure this out first. So 2 pi over 3 says cotangent, instead of y over x, takes x over y. Negative 1/2 over square root 3 over 2. If we rationalize and we simplify the 2's, we're going to get negative square root 3 over 3. Now, what do inverses give you? Inverses give you out angles. And so we can ask that question. We pull out a table if we want. If you're going to use a table, it is often easiest to think of it this way. Tangent inverse of negative square root 3 over 3 equals theta, if and only if tangent theta equals negative square root 3 over 3. Now, what in the world is that going to give you? Well, that probably comes from 1 over the square root of 3. So that's going to be, let's see, firstly, negative. Where is tangent theta equal to a negative comparison of y to x? Well, that goes back to our inverse. So this was able to be found no problem on unit circle, but tangent inverse is restricted. So when we're talking about the inverse now, this angle has to be from here to here. Okay, what's it mean if it's negative? That means that we're in this quadrant from negative pi over 2 to 0. We have to be here. That's got to click right now. It's got to be like, yeah, that makes sense because tangent is only negative here and here. This one's off limits for tangent inverse. It was absolutely just fine to find cotangent, no problem. But now when we start talking about tangent inverse, we used cotangent 2 pi over 3 to create this number, this y over x for us. Now tangent inverse says, okay, find me the angle, but be on the appropriate part. So from here to here, well, that's got to be, let's see, y over x, that'd be 11 pi over 6, oh, well, negative pi over 6. Oh, I almost made a big mistake. Why couldn't it be 11 pi over 6? That would be this angle. I'm not talking about that. I'm talking about this angle. So negative pi over 6. That would create this negative 1/2 divided by square root 3 over 2. That would be negative 1 over square root 3. And then we'd rationalize to get negative square root 3 over 3. So it's got to be negative pi over 6. If you have a table out, you can see that pretty clearly as well. Okay, last one. Sine inverse of cosine of negative 7 pi over 6. Find this one first. It's not a problem. Don't even worry about the inverse yet. Understand that cosine is defined everywhere. On the unit circle, everywhere. So we're not restricting this yet. So cosine of negative 7 pi over 6, well, let's think about cosine for a second. Cosine's an even function. So we could find cosine of positive 7 pi over 6. Man, I hope you remember. I hope you remember that cosine of is an even function. So cosine of opposite inputs gives you equal outputs. Says I can just switch my sign just fine with even functions. So let's find cosine of 7 pi over 6. That's right here. Cosine is going to give us the x-coordinate negative square root 3 over 2. Now is where the domain restrictions come in. Now is where we go, okay, sine inverse is talking just about these two. So we're going to say sine inverse is going to give us out an angle. What this is asking is, what angle on this interval is going to have a y-coordinate of negative square root 3 over 2? If you want to write it like this, that's totally fine as well. It's asked the same thing. Sine of what angle has a y-coordinate of negative square root 3 over 2? The only reason why I wanted you to see it this way is so that we don't accidentally go outside of the appropriate domain there. So we need to be in quadrants 4 to 1, negative pi over 2 to pi over 2. So this says my y-coordinate is negative square root 3 over 2. Sine relates angle to y-coordinate on this part for an inverse. So y is negative square root 3 over 2. That's right there. That's going to be negative pi over 3. Remember, it's negative here. And that's exactly what this equals. And this was negative pi over 6. And this was 3 pi over 4. So find your trig function first. It's going to give you a coordinate or a comparison of coordinates. Then your inverse, that's when you restrict your domain. That's why it was a little more difficult in the last way we did it, because you restrict your domain first. Here, you just figure out your trig function, restrict your domain last. Let's come back and deal with cotangent and cosecant and secant inverse, and then we're going to be good to go. All right, we're going to deal with some of the, well, lesser used, I would say, inverse trig functions, like cosecant inverse of whatever. Let's talk about what that even means. But before we do, something we're going to be using here, really, really important, is that, nicely, cosecant inverse and sine inverse, they have the same range. Domain for our root functions there, our normal sine and cosecant, that create these inverses for us. They have the same range for output. Now, what that means is that we can use a very nice reciprocal to change cosecant into sine. That's going to be very, very useful for cosecant inverse and secant inverse. Notice again, cosecant inverse has the same exact range as sine inverse, and secant inverse has the same exact range as cosine inverse. Where the problems happen is cotangent inverse. This is a different range than tangent inverse. I'm going to show you how to deal with that. It's the last example, 2 examples that we do. But for most of them, for cosecant inverse, secant inverse, no problem. Set this equal to an angle and then switch it to cosine or sine respectively. Sine and cosine, the reciprocal functions. Because these domains match up so well, it's not bad to do. We can't do that with cotangent very often, but we will in the first example, not the second. So here's our thought process. Inverse functions give you angles. That might be hard to do. Cosecant inverse of that looks like a bunch of junk equals an angle. So what angle gives you that relationship of 1 over y? Might be difficult to deal with. So let's write this as, well, the normal trig function. Now here's where the magic happens. If cosecant inverse of this 1 over y gives you theta, this is only true if cosecant theta gives you negative 2 square root 3 over 3. Because cosecant inverse has the same domain, or well, range, but domain for where one functions came from, as sine inverse, we're allowed to use, well, this nice reciprocal. Because they do, and we're not going to be switching outside of the quadrant that we're not supposed to be in. Cosecant theta equals negative 2 square root 3 over 3. Well, then sine theta must be equal to the reciprocal of that. And if we rationalize, this gives us 3 3 cancels with 3, we get negative square root 3 over 2. Wait a minute. That's actually pretty easy to find. Sine of what angle gives me negative square root 3 over 2? Now, here's why it was so important that I made you recognize that these intervals are the same, that the range or the domain of sine is the same as the domain of cosecant, where we get our inverses from. Because now you'll know where to look. Because sine inverse is here to here, and cosecant inverse was from here to here where it was defined, then this now is found on that same interval. Are you seeing it? Are you seeing the point of why they had to be the same? That way we can say, hey, this is defined only from here to here. Perfect. Sine inverse is the same thing. Let's use a reciprocal. And now we know we're on that same interval. So where is the y-coordinate? What angle gives us a y-coordinate of negative square root 3 over 2 on the appropriate range for sine inverse? Well, that is going to be, let's see, negative pi over 3. So cosecant inverse of this junk is negative pi over 3. You have to match up those domains. So we're going to say, yeah, all right, this is true. This is true. Then this has to be true. Cosecant theta equals that. Let's do a reciprocal and find it on the same exact domain that we're used to. Let's move on to secant inverse of negative 2. Let's do the same thing. Inverse functions give you angles. This is only true if this is true. So secant inverse of negative 2 equals theta if and only if secant theta equals negative 2. Well, this is great because secant inverse has the same range as cosine inverse does. That means that we can reciprocate it and look at the appropriate interval on our unit circle. So secant theta equals negative 2, then cosine theta equals negative 1/2. Let's reciprocate that. It's negative 2 over 1, no problem. Because they're on the same range, we can take a look at cosine theta from 0 to pi. Secant inverse 0 to pi, cosine inverse 0 to pi, and we're looking for an x-coordinate. Remember, cosine is talking about x here. Cosine of an x-coordinate gives us this, of negative 1/2 is 2 pi over 3. So taking a look at it, thought this is kind of hard. This is a lot easier. It's on the same interval. Let's just use that. So cosine of theta equals negative 1/2 says what angle on the appropriate domain is going to have an x-coordinate of negative 1/2. Cosine is the x-coordinate, and that's 2 pi over 3, and that's exactly what that's going to be for you. Let's try a couple more, and we're going to learn, well, what happens if these aren't in a circle? Use your calculator, but not the way that you think. So secant inverse of negative 3. Inverses give you angles. Let's write that. This is only true if secant theta equals negative 3. We go, all right, hey, secant inverse and cosine inverse are defined on the same domain there. So let's reciprocate it. If secant theta equals negative 3, cosine theta equals negative 1/3, but you go, wait a minute. I don't see an x-coordinate of negative 1/3 on the appropriate domain. That's a problem. So what do? Well, you see, most calculators, some do, most calculators don't have secant inverse on there. So when you go to plug in, you go, I have cosine inverse. Well, this will allow you to do that. And so if we want to find theta, remember that cosine theta equals negative 1/3 if and only if cosine inverse of negative 1/3 equals theta. Put your calculator in radians and press cosine inverse of negative 1/3, and that will give you a decimal approximation for this angle. That's about 1.91, but it is radians. Make sure your calculator is in radians. This is going to give you out radians. Now, how about cosecant inverse of negative 4? Well, we can start the same way. That's going to be some sort of an angle. So cosecant of that angle has to be negative 4. Because cosecant inverse and sine inverse are defined in the same range and domain for sine and cosecant respectively, let's find the reciprocal and say, hey, that's sine theta equals negative 1/4. No problem, just reciprocate it. But the problem is that between negative pi over 2 and pi over 2, I do not see a y-coordinate of negative 1/4. Well, then we can do the same thing we did here. So theta would equal sine inverse of negative 1/4. So this is a way that we can sort of get around the fact that some of our calculators won't do cosecant inverse to allow you to actually do it. So sine inverse of negative 1/4 is going to give you about negative 0.25. This is exactly negative 0.25, but that's not what it's talking about. The angle is around negative 0.25 radians. If you want a super shortcut, look here and look there. Just reciprocate it and use the appropriate reciprocal inverse function. The only one that will not work with is with cotangent. So I'm going to show you that one in just a second. All right, let's do the last two examples. Cotangent is a bit tricky. And the reason why it is because cotangent does not really match up very well with the interval for tangent as far as our inverses are concerned. Now, is there part of this that matches? 0 to pi and negative pi over 2 to pi over 2. Here's 0 to pi, negative pi over 2 to pi over 2. Yes, in quadrant 1. If you are in quadrant 1, if this is going to give you some sort of an angle in quadrant 1, then you're fine, and you can use tangent for this. So for cotangent inverse of the square root of 3, call that the angle that it is. This is only true if cotangent of theta equals square root 3. So we think, okay, that's positive. Where is cotangent positive? Well, the same place tangent is positive, in quadrants 1 and 4. That's the only place, 1 and 3. That's the only place tangent is positive and cotangent is positive. Well, that's in quadrant number 1. So we're not going to use 3. We can't use 3 because cotangent inverse is not defined there. Tangent inverse isn't defined there. It's just in quadrant number 1. And so we're thinking, what angle is going to give me a x over y of square root of 3? Now, if that's difficult, we go, I can't think about it that way. If you have this in quadrant 1, then you can do something like tangent of theta would be 1 over the square root of 3. And we could write tangent theta equals square root of 3 over 3 if we rationalize. So if that's true, and we're in quadrant 1 here, that was quadrant 1, this is quadrant 1, they have the same interval as far as quadrant 1 is concerned. You can do this. If not, then you can't. So then we'd look at where would you get y compared to an x of square root 3 over 3? Well, actually, this might be even easier. Either way you go, 1 over the square root of 3 would be taking 1/2 divided by square root 3 over 2. That's at pi over 6. This has to be pi over 6. So the only way that this actually works is if this is giving you an angle that's in quadrant 1, then use tangent. So what if it's not? What if this is not in quadrant 1? Well, then we have to find a trig function that's in the same interval as this is. That's going to be cosine. So let's take a look at cotangent inverse of negative 2. It's probably the most difficult problem we'll do here. If we did this and we said, hey, look, inverse functions give you angles. All right, we're good with that. This is true if cotangent theta equals negative 2. Let's put this negative 2 over 1. Now, if that's true, then this is going to give me an x over a y. Remember that cotangent is x over y. Why am I not dealing with this in terms of tangent? Why can't I just do tangent and do reciprocal? Here's the reason why. Where this gave you an angle in quadrant 1, this is going to give you an angle in quadrant 2. Why quadrant 2? Cotangent is only defined from 0 to pi. So from this top half of your xy axis, right there. Well, if you have a negative 2 and a positive 1, that's here. That's opposed to a positive 2 and negative 1, that's down there. That's not the right quadrant. We have to be from 0 to pi. So negative 2, positive 1. Remember that cotangent inverse is only defined from here to here. You have to be somewhere on there. Because that's in quadrant 2, tangent does not work. Tangent inverse does not work. You can't deal with it. Would have been fine if we were in quadrant 1 because it overlaps. If it doesn't overlap, see it here, it overlaps here and here. That's not true. We've got to use something else. So our x is -2, our y is 1. We know that cotangent is x over y. If we find our radius there, or our hypotenuse, that's 1 squared plus -2 squared, that's going to be the square root of 5. Remember to keep the positive there because I want to be in the same quadrant. Positive square root 5. Now, how in the world are we going to find an angle from that? If we have to actually find this angle, I don't maybe have a cotangent inverse on my calculator. If I did, I'd be done right here. I would just do it. That'd be great. This is not on our unit circle anywhere. So cotangent inverse, cotangent theta equals -2. There's nothing that's giving me an x over y of -2. That doesn't work. I can't use tangent because it's not the right domain. So what is? What's the only trig function inverse that is in quadrant 2? It's got to be cosine. So that's quadrant 4 to 1. That's quadrant 4 to 1. So is cosecant inverse and secant inverse. Cotangent inverse needs something that will work from 0 to pi. Cosine inverse does that. So we're going to go for cosine inverse. So cosine theta, let's find cosine theta. Cosine would take x over r. Well, if we don't even need to rationalize. If we take the inverse of both sides, now that'll let you do it on your calculator. You can find cosine inverse of -2 over square root 5. It's about 2.68 radians. And sure enough, that is going to put it right where we want it to be. So anyhow, but why do I say right where we want it to be? This is 3.14 radians, 0 to pi is about 3.14 radians, so 2.68 is somewhere in that quadrant 2 where we thought it was, and that's exactly the angle that we're dealing with. I know that this is probably challenging. When you have cotangent in quadrant 1, use tangent. That's fine. When you have cotangent inverse that's not in quadrant 1, that's outside of that, draw a triangle if it's not in a unit circle, and then you have to use cosine to deal with it because cotangent and cosine have the same exact domain for where we got our one-to-one functions. That also means that when you define this and find your angle, you can use cosine inverse. That's what we wanted to get to, and that's an appropriate angle. I know it's a long video. I hope it made sense. I've done a ton of examples so that I would actually teach you the ins and outs of this. I didn't want to give you just 3 or 4 because there's a lot of differences in how we deal with some of these things. You're seeing that right now. That's about as much as I could possibly give you. I think I've gone above and beyond and given you everything I possibly think of on how these functions and inverses interplay with one another. I hope it's made sense. Next time what we're going to do is we're going to start talking about equations. So I hope you're ready for it. Have a great day.